So today we will start from the free electron gas and start to consider the interaction effects, namely the Coulomb interaction. And we will go back to the quasi-particle picture that we started last time. And then after including this Coulomb interaction, we will appreciate the approach that I propose to study, namely the counting the quasi-particle number and using second quantization technique. But let's start from this fundamental, free electron, so-called Sommerfeld electron gas that you already learned from your introductory level of a solid state. But it's good to repeat what you have learned. And here we simply consider a bunch of free electrons living in a box, a cube, for example, and they don't interact. They are free, okay? So they just like a free particle, but they satisfy Schrödinger equation. Okay, so it's very easy to solve the Schrödinger equation for each individual electrons because they are free and they cannot escape from the box. Okay, so it's a well-defined quantum mechanical problem which you already learned how to solve from this quantum mechanics 1. Remember, hydrogen atom. Okay, so we don't even have a Coulomb interaction here. So it's just free electron. That's just a trivial problem. And if you write down the Schrödinger equation for each of individual electron, which should be considered as identical particle, so it doesn't matter which electron that you want to describe. So they all satisfy this Schrödinger equation, eigenvalue problems. Okay, and we don't have a potential energy term. We only have a kinetic energy, which is a second derivative of this wave function, the eigenfunction with respect to x, y, or z. And well, it's easy to solve, and this is the solution. The eigenstate as a product of those sign function, because those electrons live inside the box. So this periodic boundary condition will lead to this sinusoidal wave of this eigenstate, and you simply just take a product of these three eigenfunctions, and that will be your solution for free electrons living in a box. Okay, very simple. And since they have only kinetic energy, and they follow this kind of a quantum kinetic energy, h bar squared over 2m times this wave number k squared, and then this k squared in the three-dimensional space, the k space, is simply just this kind of a sphere, right? Kx squared plus ky squared plus kz squared. And if you study the constant energy contour of this electron energy, and they form kind of a surface, and the surface is a sphere, just indicated here. And this energy that for the maximum amount of the energy that occupied the electron is defined as the Fermi energy. So you can imagine that each dots here represent the electron state, and they could occupy, so each level you have, 2 electrons stay there, and you start from the lower energy states, and you populate all these electrons until you use up all the electron number. So this state is a state that electrons occupied where the energy is the maximum value that electron can occupy. Okay, so and that energy is called epsilon f, and there's a momentum of Fermi wave vector associated with that Fermi energy, which we call this kf, okay, because this is a sphere, Fermi sphere, and you can count how many electrons are there inside this sphere, Fermi sphere, and the way that you count this is just to count this Fermi volume and divide it by this, each individual little cube, the volume of the little cube, which is defined here, right? So which I call this delta K. All right, so you could consider, each individual electron occupy a small volume in K space, and then you simply just divide by this unit volume from the total volume of the Fermi sphere, and you multiply this number by 2 because you have a spin up and down, okay? And when you down that, you know this total number of electrons. Okay, so that's really simple, but then you could define, or you could get a relation between this number density, which is the total number of electrons divided by your real space volume, L cube. There's a relation between this Kf and this little n, which is the number density, and this is, the relation. Okay, and this relation comes from this simple calculation of the Fermi volume and number of states there. Okay, and this estimation turns out to be very good for many metals with very weak Coulomb interactions. Okay, so they are nearly free. Okay, so, and for example, you could estimate the electron radius inside of, say, a metal. So depending on all these different parameters, say, number of states and number of particles and your lattice structure, for example, and you can define the volume that each electron can occupy, and then the radius, average radius that each individual electron could reach, and we call this electron radius R0, and it's given by this. And later we will take advantage of this quantum mechanical units in order to calculate many solid state observables. And for example, we use this ball radius as a length scale, 0.5 Armstrong, and we measure the distance in an atomic scale relative to this ball radius. Okay, and so we define this Rs, which is the dimensionless radius of an electron relative to the ball radius. And these are the numbers that you could check in, say, ordinary metals. And the Fermi energy, again, expressed in terms of this Rs square in the denominator, and also the Rydberg constant. The Rydberg constant is the first ionization energy in this hydrogen atom, and so it is 13.5 electron volts. So the Fermi energy could be expressed in terms of this number multiplied by this Rydberg constant. So you can see that depending on this electron radius relative to the ball radius, and this Fermi energy, could be different. Okay, so the Fermi energy for different metals are different because they have different densities and they have different electron radius. So for normal metals, this Rs is somewhere between 2 and 5.5, and this Kf is somewhere between these two values, and the Fermi energy is somewhere between this range of electron volts. So that's just a review of your solid state 1. And we will start from here and to consider how good is the Sommerfeld non-electron gas in order to describe the real metals. And the answer is that it is reasonably good for some metals, but not so good for many metals. And therefore, we need to go out to account for the electron-electron interactions. And the dominant electron-electron interaction here is nothing but electron-Coulomb interaction. So we will estimate the Sommerfeld predictions for many metals and the real experimental observations. And sometimes they agreed reasonably well, but in many cases they don't agree very well. Okay? So this is just solid state 1. You could find this simple calculations anywhere, everywhere. It's everywhere. Okay, Kittel's, Oshkosh-Mermion, you name it. It's everywhere. So you should know that. Okay. So let's compare the Sommerfeld predictions and the real experimental observations. And the first quantity that we will compare is the specific heat of ordinary metals. And you know very well this, electrons are fermions. They satisfy this Fermi-Dirac distribution, and we already emphasized that this, this kind of a crossover of a Fermi-Dirac distribution at finite temperatures across this Fermi energy at finite temperature. And the definition of a specific heat is the derivative of this change of your internal energy with respect to temperature. Okay, so du by dt, and delta U refers to the change of your energies of the system, internal energy, and the change of energy at very low temperature is actually calculated from this estimation here that you could estimate how many excited state electrons are there, okay, above the Fermi level, and each excited state electrons carry approximately an order of kBt, that kind of a kinetic energy, okay, for example, for free electrons. And therefore, the total energy change relative to the zero temperature case is nothing but the number of excited state electrons multiplied by the kinetic energy carried by each individual excited state electron. Is that clear? Okay, so this is the kinetic energy per excited state electron. And this is the number of excited state electrons. But what is the number of excited state electrons? Well, again, you need to look at this picture again, because this is nothing but the range of this Fermi broadening, okay, above the Fermi energy, and this is given by the density of states relatively is a constant value at the Fermi level, and multiply by the width of that distribution, roughly speaking, right? So the density of states is defined by the number of states per unit energy, and therefore the total number of states is given by the density of states times the the range of the energy, and the range of energy above the Fermi level or below the Fermi level is the same. It's about kBt, right? And the density of states near the Fermi level is a constant, valued. And since the temperature is very low, you can simply just use this as an approximation to approximate the total number of excited state electrons by the number of, the density of states multiplied by the window, the width of the broadening in Fermi distribution. And this is nothing but density of states times the kBt, but there is another kBt carried by each individual electron in the excited state. So the total energy change relative to zero energy case is this, this product, this. Okay, so you simply take the temperature derivative of this delta U, and you get something which is linearly in T times some constants. So here comes your homework. So use the Sommerfeld model to actually derive the exact formula for the specific heat. So this is the exact expression. So remember, this is only estimation that I did here. So it's not exact, but for the sake of the order of magnitude estimation, this is good enough. But this is not the accurate value. So this is the accurate value. And derive it. Okay? So again, this is just a review of a solid state 1. So this is the prediction from the Sommerfeld model. And what about the experiments? Well, experiments has this very similar form, but with some modifications on the electron mass. So we need to assume a different electron mass, so-called electron effective mass. Effective electron mass. Electron effective mass. We need to assume electron mass which is different from the free electron mass in order to really compare these two. So let's just perform this comparison. So if I take the ratio between the CV experiments and to the CV free, and what I get is nothing but the ratio between the effective electron mass to the free electron mass, because all the other factors are exactly the same. You could really compare. Okay, so this is from experiments. Okay, and this is a Sommerfeld electron gas prediction. So let's see the difference for different metals. So this is 1.5, and okay, so type of metal. 1.5 is what's copper, silver, and 1.2 is tin and lead. Okay, so you could clearly see that some metals could be described very well by the Sommerfeld model. For example, this silver. So for silver, the effective electron mass is precisely the free electron mass. So you could consider the electrons in the silver are free, almost free, because they are identical. Okay, these two values are identical. However, for other metals, they are not so bad, but they are not so good either. For example, for copper, this ratio is actually 1.5, meaning electron mass inside copper is actually heavier by a factor of 1.5 relative to the free electron mass. And for the lead, and this ratio is actually 2 or 2.1, and this is even worse. So, which means that this Sommerfeld free electron model, I would not say it fails, but it's not good enough, because then this ratio is not 1. So this is a perfect match, but this is questionable and questionable. Okay? And the reason why they have such a deviation is, as I mentioned, because of the Coulomb interaction, which is not included in this very naive Sommerfeld model. And the Coulomb interactions is actually very important to understand low temperature properties of solids, and we will emphasize that as we go on. Any questions? Yes?
Are there any metal lower than 1?
You mean this ratio is more than 1?
Lower.
Lower than 1. Yes, there's 0.9 zinc, and I think this is calcium, this 0.8. Okay, so they're not so bad. So they're very close to 1. But you can you can ask why these values are smaller than 1. Okay, so I need to check the textbook before I can answer that questions. Okay. Yes.
As a memory, the silver near the Fermi level seems like the orbital, but it seems it's the best value for compared to the experiments, right? Because the 1.0, but silver it seems the orbital. In your opinion, the orbital is a free electron.
That's a good question. So, is the d orbital the conduction orbital for a silver? Well, of course, I mean, you could check your periodic table whether is this the case that silver, the conduction electron come from the d orbital. Of course, I agree that d orbital may suffer from Coulomb interactions. So that's your question, right? Why is the Sommerfeld model so good if to describe the d electrons? Well, I need to think about these questions, but you could check your introductory solid state textbook that the silver is a very good conductor, so that's for sure. And then I think some d orbital electrons could I shouldn't say that they don't have the Coulomb interactions, but I can clearly see that the effect of Coulomb interactions is not big, at least it's not strong. Okay. Maybe there are some cancellations, here and there, so that this is exactly 1. So I think this is an interesting topic, but we will discuss that when we get there. All right. So, any other questions? If not, let's look at another quantity to compare, which is the Pauli spin susceptibility. Okay, so you know very well that the free electron form a Fermi surface, and for ordinary metals, they have this kind of fully occupied states for each individual level with up and down spins populating there. And the Fermi energy is the energy where the highest energy of electrons can actually populate, and this is only a partial filling. Okay, so say the band gap is somewhere here, as we mentioned, but the number of electrons is not that large, so that they could only fill up partially in a lower band. So that electrons could actually get excited very easily, and that's how the metal works. But imagine that we apply the magnetic field, and because the magnetic field coupled to the electron spin, so that the up spin states have different energies relative to the down spin states. Okay, because of the Zeeman energy. When we do so, the dispersion of this free electron gas get modified, and this is the shift of the energy band by plus and minus mu b. So the electron energy with the spin up states get shifted what? Upwards. And the downspin electron dispersion get shifted downwards. Okay, but the Fermi energy is still the same because they are the same path. They belong to the same electron path, so they have the same chemical potential. But then the electrons, all the electron states, are separated into two different groups. Okay, so one group is the spin down state, where their dispersion gets shifted upwards, but the downspin state shifted downwards. Okay, so then you get imbalance between the number of spin up states relative to spin down states, because if you have the same chemical potential cut through this dispersion, then you immediately see that there are more downspin states, downspin electrons, relative to the upspin electrons if you have such a Z-band field applied to the free electron band. All right? And therefore, you get magnetization. So the number of spin up state is actually 1/2 m minus, and the number of spin down state. As a result, you have a magnetization which is defined by the difference in the upspin electrons and the downspin electrons multiplied by your magnetic moment. And this is given by density of states mu square V. And you could then define so-called the Pauli spin susceptibility, which is the differentiation of your magnetization with respect to these small magnetic fields that you applied, and which is mu square times density of states. So this is something that you can measure in the lab. Okay, so you put a piece of metal in your lab, and then you lower the temperature, and then you apply the magnetic field, and you measure the magnetization, and then you take differentiation of the magnetization with respect to the field, and you get the susceptibility. So that is a measurable quantity, and then you could again compare this value, this measured value, with the Sommerfeld prediction. So what you get. So let's just summarize the comparison: lithium and sodium from the free electron. So this is, and from the experiments, this is. Okay, so in the proper unit, the free electron Sommerfeld theory predicts this chi Pauli to be, say, 0.8 for lithium, and for sodium, this 0.64. But in the real experiments, this chi for lithium is about 2, and for sodium is about 0.9. Okay, so there's some difference which cannot be ignored. Okay, so what are these differences? Well, so you will see later that the difference may be due to the Coulomb interaction, but there are some other interactions, such as spin-related couplings, okay, which may lead to such a noticeable difference between the experimental observation and the Sommerfeld prediction for the spin susceptibility. So therefore, this again justifies the need that we need to more carefully address the interaction effects in solids. And the way that we address these interactions is to perform the second quantization approach, and we count this quasi-particle number, and then we sort of ignore all this kind of stable states, and which will not participate these low energy excitations. Sorry, there's no B. It should be this, right? Okay. Yeah, thank you. Let's take a short break. When we come back, we will introduce the idea proposed by Landau to actually describe this weakly interacting electron gas. So we know that these electron interactions are present, but when they are weak, we can still use sort of a free electron picture to describe such electron states, and they are called Landau's Fermi liquid picture. Okay, so let's take a short break. So far, we simply just use a very naive Sommerfeld model, and we compare this prediction to the real experiments, and we found that there are some deviations, and we need to address that. And in fact, Landau already noticed this. And it's called Landau's Fermi liquid picture. So in the 1950s, Landau realized that, of course, the free electron model is not sufficient to describe the real metals, because the real metals, there are electron-electron interactions. However, if such electron interactions are weak enough, then we can still take advantage of the Sommerfeld free electron picture to describe such a weakly interacting electron gas. And Landau's Fermi liquid picture. So again, as we pointed out, that relative to the Fermi level, there's a thin shell below and above the Fermi level of an order of kBt, where the electrons can get excited and participate in this kind of elementary excitations. But we know that those electrons are not completely freed, so they interact by Coulomb. Okay? But if such interactions are weak enough, and Landau say that we more or less could actually consider them as independent free particles, but we need to modify their mass and dispersion. So Landau says as interaction turn on adiabatically or very slowly, and the Pauli principle makes the ground state of the free electron gas unchanged, but we need to modify the band dispersion. So those parameters, electron band dispersion and electron mass and ion mass, are all subject to some renormalization or modification to a new value, okay, under such a electron-electron interaction. And suppose these interactions turn on very, very slowly, and so that this won't disturb the system too much, and then this kind of a Sommerfeld free electron model is still very useful. And then we could have such so-called the elementary excitations to get some kind of a modifications So coming from this free electron model to Landau's Fermi liquid picture. Remember, we have this electron hole pair excitations, right? Above and below the Fermi level. Suppose all these electrons are free, then we simply just have a single electron excited state above the Fermi level, and that electron is actually the same electron that we consider as a free electron. However, in the presence of a Coulomb interaction, so these electrons are no longer free. However, as Landau pointed out, we only need to modify the band dispersion and electron effective mass, and then we can still consider this as an independent, called a quasi-particle. Okay, so this quasi-particle is kind of almost free. It's like a particle, but with dress up. Okay, namely, this electron hole pair will actually interact with the other electron hole pairs or other electrons, so that this single electron picture is not, it's still valid, but this electron gets heavier if this electron interact with the other electrons. So this electron mass is actually heavier than the free electron because it interacts with the other electrons. It's kind of dragged by the other electrons, and so that it carry a bag, a heavy bag behind each individual quasi-particle, so that it moves slower. Okay, more slowly, and it's like Santa Claus carrying a bag, and that is the concept of the quasi-particle. But they are still considered as the free particles. Okay, but they are, sort of an independent particle, not free. You can consider this quasi-particle as the free particle, free electron carrying a bag behind them. Okay, and that makes these electrons heavier. And so again, this ion mass will get modified to a new value, m star, which again is actually greater than this ion mass if we don't consider the electron interactions, and electron mass get heavier. And this band, because of the electron mass get modified, the bands also get modified, because remember, electron mass gets updated or get heavier, so that the band dispersion gets flatter. Right? So that's the only changes that we can imagine if weak electron interactions are included in the Sommerfeld free electron model. And one more thing, which is very important, is that the quasi-particle lifetime, this electron hole pair, can actually live forever in the free electron model, because there is no Coulomb scattering. So we will come back to this in just a moment. Okay, so they actually live forever in the case of the free electron gas, but in the case of this Landau's Fermi liquid, this quasi-particle actually has a lifetime. So tau refers to the time that this quasi-particle can live without decaying. Okay, so you can imagine that this electron, if they interact, it interacts with the other electrons, can actually fall back to this inner shell if there is a hole, and so it could actually fall back. okay? Or it could actually scattered by the other electrons, so that this electron can actually decay into the hole inside the Fermi sphere, so that this excited state electron is gone. It's called decay. Quasi-particle can decay. But imagine if the electrons are completely free, then none of this process will occur, so electron can actually stay there as long as it takes, forever. Okay? So it's called long-lived quasi-particle if the electrons are free. But in the case of weakly interacting Fermi liquid, then the quasi-particle acquires a lifetime, which means that they will decay, even though they could live very long, but they eventually will decay. And there is a finite, less than infinity, that a long lifetime associated with each individual quasi-particles. Okay? Therefore, if you measure this, excited state electron over there, in the case of a Fermi liquid, it can only stay for some time. And if you, measure this decay time, you'll find that this is finite, not infinity. Okay, so mathematically, we could formulate such a kind of a decay of a quasi-particle in quantum mechanics. Suppose we have such a kind of a quasi-particle, and we call this psi. At 0 is generated, and we could use the quantum mechanics to actually estimate the overlap of such a excited state electron at the later time t with the initial states, that's when this quasi-particle is just generated. Okay, so you could actually find this overlap or this probability to find this quasi-particle later time t. Okay, if this is the constant, then this will not decay. But if this is the decay function time, then it will decay. So this quasi-particle energy in the presence of the interaction carry a so-called imaginary part of the self-energy. So we will talk about the self-energy later, but here I'm just telling you how to mathematically understand such a decay of a quasi-particle in quantum mechanics. So the way that this quantum state can decay is because it has the imaginary value in their energy. Okay, so based on the quantum mechanics, you know that this is proportional to e to the I epsilon p t divided by h bar. Right? So if this epsilon p, which is the quasi-particle energy, carry the real part, which is the free electron kinetic energy, and the imaginary part, which is the decayed part. Okay, and then it will decay. Okay, so let me just show you how this decays. So this is given by, you see? So the first part is nothing but this, Schrodinger wave function, the plane wave-like oscillatory function of time. And the second part is the decay part. So in other words, the modification due to the weak interactions in the free electron gas is the modification of a dispersion or excitation energy of each individual quasi-particle. Namely, they acquire an imaginary part in their excitation energy, which will lead to a decay of a quasi-particle in time because of this imaginary part. So that's also a prediction by Landau's Fermi liquid theory, that the quasi-particle will decay. And the way that they acquire such an imaginary part, is a different story. So we need to actually calculate the self-energy of an electron in the presence of a Coulomb interaction, but we will do that later. So here, I'm just telling you that this is different from the free electron prediction because we have a finite lifetime of a quasi-particle. Because gamma p is non-zero, so that this tau in the presence of the interactions is a finite, okay, less than infinity value. Okay, so that some electrons will decay and the quasi-particle will not live forever. So let's take a short break. When we come back, we will start to introduce this quasi-particle picture again. Okay, so based on what we just learned, the Sommerfeld free electron model and also Landau's Fermi liquid picture, so we can understand the low temperature resistivity for ordinary metals because of the Coulomb scattering behaves as a t-square. So this is a success, a very big success of a Landau's Fermi liquid picture, which is a prediction of a t-square dependence of electrical resistivity for ordinary metals, and which is precisely what experiments are shown. Okay, so we know that the pure metals will become superconductors when temperature goes zero, but before they become a superconductor, the resistivity drops as t-square. And we will argue based on the Pauli principle and this, kind of a Fermi surface picture like this, and we could, sort of without sophisticated calculation, we would know why this resistivity goes like t-square. Okay, so this is a magic, and you will appreciate this kind of a hand-waving argument, but it's very physical. So let's take a short break. When we come back, we will study this. Yes?
Does the self-energy just like potential?
Well, it renormalized the kinetic energy. So remember, this is a kinetic energy, right? So it is the kind of a contribution to the electron kinetic energy coming from potential energy. It's a correction to the electron kinetic energy from some potential energy. You know that, right? So because of a Coulomb, it will lead to some modification of the electron kinetic energy, and that's precisely this imaginary part. Okay? So by the end of the semester, you will understand how this mysterious imaginary self-energy come from. Okay? Just be patient, and you will understand that. And this will be a big triumph for your understanding, because I believe that most of you did not think about this in that way. All right? So again, so we will take advantage of a second quantization and to actually calculate this electron self-energy, and you find that this is indeed an imaginary value, and that proves this decay of a quasi-particle. So let's study this Fermi liquid theory of electrical resistivity in ordinary metals, which goes like t squared and we go back to this very important cartoon picture that we repeated over and over and over again. Okay, so this is the most important picture for the first part of this course. And we know that some of the electrons just below the Fermi level could actually go excited to the excited states within that shell above the Fermi level, and they become the quasi-particle electron-hole pair. But then these electrons, inside or outside of this, Fermi level, but within the same shell, can actually interact with each other. And so this is a standard so-called diagram where you get the two-body interaction, right? So like Coulomb scattering, and two electrons get closer, and then because of the Coulomb potential, they get scattered out and they move towards different directions after scattering. So that's the cartoon picture of a two electron Coulomb scattering, and here is the same. And then they will get scattered. Okay, so this is epsilon p, and this is epsilon 2. So they could get Coulomb scatter. Okay, so after the scattering, most likely these two electrons will become the excited state electron above the Fermi level, and epsilon 3 and epsilon 4. I don't know which one is which, but from this kind of a Pauli principle, we know that the scattered electrons most likely live outside of the Fermi surface. Anybody know why? You'll get a bonus point. So the question is, why do I consider these two electrons after scattering the excited states, not the occupied states? 为什么我考虑散射过后的两个电子是在费米面的外面，不在里面？ Do you understand my question? So let me give you a hint. You will know what I'm talking about. So what I'm doing here. Anybody know why I shaded this this area by the blue? It's very simple. You just, you don't think about fancy stuff. You think about what we just discussed, the Pauli principle. So what the Pauli principle tells us. So what is the common feature that I shaded here? These are the states which are empty or occupied. Occupied. If they are occupied, can they get inside? No. That's simple. But what is the percentage of the states that are occupied inside the Fermi surface? Well, it's almost 100%, except a few holes. Remember that, right? At low temperature, so there's some percentage of electrons, below the Fermi level can actually go out, but some, it's like a qualitative description. In quantitative language, it is actually few percent, even 1%. Okay, suppose there's just 1% of electrons below the Fermi level which can actually go out and leaving behind holes, and the rest of the 99% of electrons are occupied. If they are occupied, it's forbidden by the Pauli principle that the scattered electron will go inside the Fermi level. Is that clear? 我再用中文说一次，因为我蓝色虚线标的地方是电子填满的地方，因此包粒不相容原理，如果外面有两个电子的话，它进不来，因为包粒不相容原理禁止已经被填满的电子再填到同一个 state， 对不对 ？Do you understand? Okay, and therefore the scattered electrons should be outside of the Fermi surface. Okay, as a result, epsilon 3 and epsilon 4 are both greater than epsilon f. So now let's estimate the probability of such a scattering event, which is inverse of the lifetime. So the inverse of the lifetime is a probability of a scattering event, or a scattering probability, which is kind of two processes. First, you need to estimate the number of available states And also, you need to estimate the number of empty states. Okay, so number of available states is nothing but the states, number of states inside this inner shell. So the number of available states is nothing but this orange area, where you can pick any states you like to be epsilon 2, for example. So how many choices do we have? Well, the number of choices, is proportional to the area or the volume of that inner circle, right? Inner shell. But what about the number of empty states? So the number of empty states is the number of choices that you can have to actually pick any particular states out of the Fermi surface. But again, you have a conservation of energy. Okay, so therefore you only have 2 degrees of freedom left. The 1 degree of freedom is the degree of freedom that you choose your initial states, and another degree of freedom is the degree of freedom you choose the final states, just 1 electron state. And the total probability is nothing but the product of these 2 probability, right? Okay, and each of the probability is proportional to the phase space volume, which is this, the volume of this inner shell, states, and also the volume of the outer shell states, which is this stuff. Okay? So from your statistical mechanics, you know that this total scattering processes is nothing but the product of these 2 individual scattering probabilities. So let me ask you another question. So in terms of the temperature, what is the number of available states in terms of temperature? So in terms of temperature, so how do we estimate the number of available states? Well, let me give you a hint. So what is the width of this ring? Yes? Yeah. And what about this? Another KBT, right? So I don't care about the other factors. I only keep the most important factor, which is KBT. So each of this ring or inner shell contribute to 1 factor of the KBT to your scattering probability. As a result, the total scattering rate is proportional to T squared. And that is precisely this T squared that you measured in the electrical resistivity of ordinary metals at low temperature. You see? This argument is really elegant, beautiful, no complicated mathematical calculations, but only physics, the Pauli principles and Fermi surface and elementary excitations. And you know this T squared over electrical resistivities in ordinary metals. So then this tells us that because of electron scattering by Coulomb, and the electrical resistivity depends on temperature, and it decreases as T to the power of 2, T squared fashion. And namely, if temperature goes 0, then electrical resistivity will drop to 0. But before it drops to 0, like T squared, it will actually decay exponentially to 0 when you reach the superconducting temperature Tc. So this is really what happens in ordinary metals. There's a T squared decay of electrical resistivity up to Tc, then it drops exponentially to 0. It becomes a superconductor. Okay, and then we understand how this behaves, why this is so, because of this Coulomb scattering of elementary excitations. Okay, good. So let's just look at another very important features of this lifetime. So suppose that these two electrons, epsilon p and epsilon 2, are located exactly at the Fermi surface, which means that both energies are exactly epsilon f. And then what happened? So that's very interesting question. Suppose that both electron states are exactly here and here, epsilon 2 and epsilon p. Can they interact by Coulomb? Can they get scattered by Coulomb? Okay, so you can think about this. So, the way that we check whether they could get scattered by Coulomb is to check whether they can satisfy the scattering condition, namely this energy conservation condition. Because it looks suspicious, because when both of them are exactly epsilon f, then we have a trouble satisfying this energy conservation, because epsilon p plus epsilon 2 is actually 2 times epsilon f, right? They are identical. But we assume that both epsilon 3 and epsilon 4 are out of the Fermi surface, right? Where this epsilon 3 and epsilon 4 is actually greater than 2 times epsilon f, right? So how come 2 epsilon f is actually greater than 2 epsilon f? It's not possible. So you cannot satisfy this conservation law of scattering processes. And therefore, there's no such a scattering possible to exist. Because it's impossible to satisfy this energy conservation. Suppose we consider both epsilon 3 and epsilon 4 are out of the Fermi surface, and this immediately tells us that this tau is actually infinity, because no such scattering is possible. If they don't scatter by Coulomb, they can stay there forever as long as they want. Okay? Good. And that's a very good indication that if, suppose that these two particles, 2 electrons, are very close to, but not exactly at the Fermi level, but as close to as Fermi level as possible, then they can live as long as they like. So this lifetime becomes longer and longer and longer if these 2 states are closer and closer to the Fermi level until they exactly touch the Fermi level and they live forever. So now you can see that these 2 are actually closely tied to each other. The lifetime of quasi-particle depends on where these 2 initial states are. If they are exactly the Fermi level, and they can live forever. And that's precisely the Landau's Fermi liquid picture, saying that the quasi-particle shows a very long lifetime near the Fermi level. Okay? So they could actually live almost forever. And this is just an extreme limit where they are indeed living forever if they are exactly at the Fermi level. But can we consider them as a quasi-particle if they are exactly the Fermi level? Probably they are not qualified to be a quasi-particle because they are considered as just a fully occupied electron states. That's all. There's no excitation if they are just sitting there, because there is no excitation energy, right? But we could just deviate from this extreme limit just a little bit, and we could argue that this lifetime is very long but still finite. Okay? So here comes another homework problem. So here I'm just using the hand-waving argument, okay, based on the phase space volume that the scattering rate is actually the product of these 2 probabilities, and each of them contributes to kBt, so we have t squared. But you could also estimate this in a more accurate way, that 1 over tau is actually kBt square pi square h bar square and kf square, which is a h bar inverse kBt square, and find the prefactor a. So go back to the Ashker-Fermion or Kittel's or whatever textbook you can find, and to more accurately, estimate the scattering rate, and you will find that this, 1 over tau is proportional to all such a messy prefactor, and when you clean up all these, factors, you will get some prefactor a, and find out what this is. And the typical tau for ordinary metal is about 10 to the minus 10 seconds. Okay, the typical, which is very short, but still, long enough because, if you consider this as femtosecond, picosecond, attosecond, so you could try that, but in many solid-state systems, the time associated with this is actually much smaller than this 10 to the minus 10. So it is not a long time, but it's actually long enough to be observed. Okay, is the lesson that we learned today. Okay. Any questions?
我想问我可以说这个系统是原本是从 n 个 particle 的系统变成 n 加1个 particle 的系统
Well, the answer is no, because remember we have a total number of n electrons. It's just where they are. Okay, initially they are all inside the Fermi sphere, but as you turn on temperature, some of them get outside of Fermi surface. But these electrons can actually interact with the electron inside the Fermi surface. So that's the only difference. You don't increase the number of particles. It's just they are redistributed in the different energy levels as you turn on the temperature. All right? Okay. Any other questions?
Yes. Why don't we consider about the process which E2 and EP swap?
E2 and EP what?
Swap. Exchange.
Exchange E2 and EP.
Yes. Because it doesn't contribute to the conductivity or other reason.
You just relabel this, right? Nothing is changed. I call this 2 P, and I call this P2. Whatever name I call this, it's the same. What is your real question?
The real question is because you consider the process one electron inside the Fermi surface.
Yeah, good question. So you could think about if 2 electrons are out of the Fermi surface, right? Or 2 electrons are inside the Fermi surface, right? Okay. I don't assign this to you as a homework exercise, but you can think about that. Okay. So why do I consider 2 particles, one inside and one outside of the Fermi surface? And why not 2 of them are out of the Fermi surface, and why not 2 of them inside the Fermi surface? So the answer is still Pauli principle. Okay? So what is the probability that you can find the 2 excited states outside of the Fermi surface? Is it close to 100% or close to 0? Close to 0. Okay, if you start from the initial state, which is close to 0 probability, and you forget about this, right? So likewise, what is the probability that 2 electrons inside the Fermi surface can interact with the states out of the Fermi surface? While they are happy staying inside the Fermi surface, they don't want to interact. Okay? So again, this probability is very low. So then we could thrown away. And therefore, the most probable scattering situation is 1 in and 1 out. Okay, so which gives you a sizable probability, and which is precisely the dominant contributions is from. So you can still estimate the probability of this case and that case, but the prefactor is actually almost 0. Okay, so I'm saying that this is the leading processes that gives you the leading contributions to the electrical resistivity, 1 in and 1 out as initial state. But this is a very good question. You see, everything could be understood in terms of the Pauli principle and the Fermi sphere. So this picture should be imprinted in your brain, and it should appear in your dreams, so that you could really, understand this physics. I guess time is up, but on Wednesday we will introduce the concept of this counting of a quasi-particle. So now you know the background, and you know why we will count this quasi-particle, because, right, there are not so many. So the remaining part of the states are fully occupied, and they are all stable. So they don't participate in these low energy excitations. So we can, forget about them altogether. And we only focus on these states just, inside and outside of the Fermi surface by a tiny, thin shell window. Okay? So this is the starting point of the second quantization, and we need to count how many particles are there at low temperatures of metals. And we need to define mathematically how to create or destroy a single particle in that picture. Okay? And we need to rewrite Schrödinger equations in the Dirac notation, and we will play some tricks to actually transform the Dirac notation into a kind of a creation and destruction of a single particle, and the purpose is to count them. Okay? Good. So I think that's perfect ending of our introduction to the advanced solid state too. So now you know the reason why we need to count the quasi-particle. Okay? Good. So I'll see you on Wednesday.